Let's jump right into this explainer. We're looking at a genuinely fascinating classroom scenario. Seventh graders taking a seemingly simple, everyday object and completely deconstructing it. Through structured, scientific sense-making, they unpack a surprisingly deep mystery about matter. We're going to focus in specifically on what these students figure out, how they organize their chaotic brainstorms, and how they build an incredibly powerful tool called an initial consensus model to guide their whole investigation.
It all starts with something you've probably seen in your own bathtub. You drop a solid bath bomb into a bowl of water, and immediately it starts vigorously fizzing. It's super common, right? But when we actually stop and look at it like scientists do, it instantly becomes a puzzle. What exactly is going on in that water?
Section 1. The Macroscopic Mystery. So, by carefully observing this whole fizzing process, the students establish a few core facts. This creates a shared mystery that just begs for an explanation. They see the solid breaking apart and eventually disappearing. They see vigorous gas bubbles appearing literally out of nowhere. And, crucially, if they check a thermometer, the liquid actually gets slightly cooler. That temperature drop is a subtle but absolutely massive clue that the kids note down.
But what is happening to the matter at a scale way too small to see? This hits on that classic pivot every scientist has to make. We have to move from what we can clearly observe in the bowl to the completely unobservable mechanisms that are actually causing it. To crack the bathbomb mystery, the students realize they have to zoom way, way in and imagine this entire system at a microscopic particulate level.
Section 2. What students figure out.
When the students start brainstorming, you see some intense, awesome scientific debates taking shape. They're throwing out questions like, does it dissolve? Does it react? Were those bubbles already trapped inside, or did they just form? It's a beautiful, chaotic display of authentic scientific sense-making in action.
First up, we've got competing ideas about the solid matter itself. Did it melt, or did it dissolve into the liquid? Now remember that crucial observation we just talked about, the water getting cooler? Well, if the bath bomb were melting, it would actually require an increase in temperature. Heat would need to be added. Since the water cooled down, the students have this great early piece of evidence to challenge the melting claim, pushing them toward the idea that it's either dissolving or reacting.
Section 3. Competing Ideas about Matter.
Then there's the gas. The students realize they're stuck between two highly competing theories here. Was the gas just hiding inside tiny pockets within the solid bath bomb, just waiting to escape? Or is it an entirely new substance forming right before their eyes from a chemical reaction? The wild thing is, both of these theories perfectly explain the macroscopic fizzing we see, but they represent totally different realities on a microscopic level. So how do we organize and represent all these diverse, competing ideas? With all these conflicting theories flying around the room, the students desperately need a structured way to sort out exactly what they know and what they absolutely don't. You can't just leave a mess of ideas on a whiteboard. You need a real framework to figure out the next steps. Section 4. The Initial Consensus Model. And that brings us to the consensus model. This is a visual, scientific tool used by a community to identify areas of collective agreement, clarify uncertainties, and explain unobservable mechanisms. The goal here isn't to be perfectly right on the very first try. It's to establish a baseline of what the entire class agrees on, and, maybe even more importantly, to explicitly highlight their controversies. It's not just a drawing. It's a powerful engine for collective sense-making that literally turns confusion into actionable science. The students work together to sketch out an incredibly detailed initial consensus model, representing the microscopic particle level of the bath bomb system. They draw outer circles to show what they think the particles look like in the solid, the liquid, and the gas states. But the most important part is right in the center. A large area filled with question marks, representing the unobservable mechanisms they are still actively arguing about. For the agreements, the students pull from their past learning. They successfully agree on the spacing of the particles. Solids are closely packed together, gases are spread far apart, and the liquid is likely a mixture of water and whatever the bath bomb left behind. Establishing this shared foundation is a huge win for the class. But then we hit those areas of controversy in the model. Are the gas particles the exact same material we started with? Is the solid breaking apart, melting, or reacting? Was the gas just released, or was it newly generated? By putting these massive questions directly into the center of their consensus model, they give themselves a crystal clear target for their upcoming experiments. Because in science, disagreement drives investigation. It's absolutely crucial to recognize that these exact disagreements are what motivate the kids to go find actual evidence.
If everyone just agreed right away on where the gas came from, there'd be literally no reason to run an experiment. The consensus model proves that confusion, when it's organized properly, is the ultimate engine of scientific discovery.
Section 5. The path forward.
So the students translate all those uncertainties into a concrete action plan. They start brainstorming initial ideas for future investigations. Things like looking up the actual ingredients used to make the bath bombs, or testing those individual ingredients separately in test tubes. Someone even suggests dropping a bath bomb into a completely different liquid, like oil, just to see if water is actually required for the fizzing to happen. They are actively designing ways to isolate the variables. Armed with their newly built driving question board, their consensus model, and a bunch of competing theories, the real detective work is just kicking off. They know exactly what they agree on and exactly what they're fighting over. But it leaves us with one massive, lingering question. How do you actually design an experiment to see the invisible? How will they ultimately prove which microscopic model is the right one? Well, that's a mystery for another day.